Okay, now on to the last part of the talk, and much of what I've had to say has been covered, at least in part, by the previous two speakers, which is excellent. What the slide I've got up here is some of the questions that are often framed in a sceptical context regarding the costs of climate change, and it's been covered a little bit by David and Gavin already, some of these issues, which is good. So, from the delay tactics of let's wait and see to the idea that Kyoto is a big effort, doesn't do anything, or why should Australia do anything because China and India are the problem. Climate change mitigation will ruin the economy, population is the problem, offsets don't work, we can't upscale renewable energy, technology will fix the problem on its own, we can geoengineer or bioengineer our way out of the problem, or issues about carbon capture and storage. So let's explore some of those ideas. But first, more fundamentally, let's look at that idea of population growth and whether that's the cause of the problem or the solution to the problem. The world is highly populated now. It's got about 6.5 billion people, a growth from about 1 billion in the start of the 19th century. Historical growth is now being superseded in new areas by modern growth. So a lot of the growth is now coming from Africa and South Asia and South America, whereas historically a lot of it came from East Asia and Europe and North America. So the human population is huge now, it's burgeoning and it's continuing to expand, albeit at a lower rate, might reach about 9 billion by 2050. If there was only 100 million people on the planet, we wouldn't have an issue right now. But the fact that we've got 6.5 billion means we have got an issue. However, if we want to correct that problem, then it's not something we can do immediately. It takes literally generations to turn the human population around unless you take rather more radical steps. So with that 6.5 billion people, we're having major impacts. Every extra person you add, especially if their footprint is large, will have a huge impact. It will increase the demand for fossil fuels, the demand for natural products such as wood, so it will increase rates of deforestation. As there's greater demands in agriculture to deliver food, we'll have problems of soil degradation, increasing amounts of waste to dispose of, both commercial waste and other industrial forms of waste, including greenhouse gases and nuclear waste. So there's been a lot of discussion over the last decade or two about this concept of sustainability then. And sustainability being this concept of embracing the triple bottom line. So rather than just considering economic profits and cost savings and growth, thinking about that in the context of the environment and in social aspects such as standards of living. And at the nexus of those, of course, there's a Venn diagram for everything. Here's the one for sustainability, where it sits at the nexus of those three elements of society and the environment and economy. Another way to look at it, the figure on the right, is to consider the economy as a subset of society, which in itself is a subset of the environment, because we require so many environmental services to allow our society to exist. There's many ways in which you can consider our impact on the planet as a whole. One of those, which has got some traction, is known as the ecological footprint, which essentially is an integration of all of our demands on the planetary system, not just carbon emissions, but food demands, impacts on biodiversity, impacts on the oceans, pollution, and so on. The best estimate for that is that there's a huge global change in global distribution in terms of overall impacts, where some parts of the planet they're quite low and other ones are very high. We've got South Australia sitting over there. Most of the developed world has a high impact over here. Most of the developing world has a low impact. The black line there is the global average, which on our best estimate is perhaps exceeding what the planet can supply by about 25% right now. And of course, as you start to erode your capital, just like money in a bank, the capital will earn you interest, but once that capital starts to be eroded, in other words, you're taking out more money than the interest it's generating, then the capital starts to decline and you generate less interest over time, and in the end you get into a sticky situation. To grow economies, in the modern context, essentially you need energy, and you need more and more energy to do that. And so, depending on who you listen to, the relative supply of energy in the future will come from fossil fuels or nuclear or expansion of renewable energies. Most of these scenarios project large growth in energy demand, whichever one you accept as being the major contributors. If it is contributing mostly from coal and oil and gas, then we will continue to have rising carbon emissions, as we've seen over the last 150 years, and most dramatically over the last 10 years or so, where we're now tracking well above the highest end projections made a decade or so ago. That demand for energy is not going to go away even if we ignore the climate problem. This is some projections from the World Energy Outlook produced by the International Energy Agency, just looking at the demand for energy growth even without any consideration of the climate. And their estimate is that by 2030 we'll need to invest an additional $20 trillion globally in terms of replacing aging infrastructure and building new infrastructure to supply the additional energy demands. So that's without even building a single more solar power station or another wind turbine. It's just the amount of demand we're going to need to supply our growing economies should they continue. And when you need to do that, then you need to build in the capital costs of things like building a new coal-fired power station or a gas turbine, and they're expensive. What we often get shown is the cost of generating power from coal without considering the levelized cost, which is the total cost of the life cycle, which includes the cost of building the plant, which is in the range of $1,000 to $2,000 per kilowatt capacity that it can generate. So when you build in those total costs, the figures can often be quite different to what would otherwise be reported. It's not just energy, of course, that's rising. As the population rises and GDP globally rises, then all these other metrics that you can imagine associated with the modern economy continue to rise exponentially. The damming of rivers for water supply and water use, fertilizer consumption, paper consumption, transport and motor vehicles, telecommunications, McDonald's restaurants. You think about just about anything you can imagine in society, and that's rising. But if you look at the planet from a great distance, this is a famous photograph from Voyager, taken at about 4 billion kilometres, then you find everything we need to supply our needs is in that little dot, suspended in that sunbeam there. So, in fact, it's quite patently, clearly a finite resource. It's just a matter of how much of that finite resource is remaining, and therefore it's not a question of can we continue to exploit that resource forever. It's a matter of how long can we continue to exploit that resource, and at what point does the crunch come? Or alternatively, are there ways of exploiting the resources on that planet that take account of inputs to the planet, which is mostly solar energy, that can continue to allow us to persist essentially indefinitely? That's the concept of sustainability. Now, if you look at fossil fuels, they're one of those examples of a limited supply. Next session, in the last session in 2 weeks' time, Michael Lardelli will talk a lot about this issue, which is the idea of a peaking of fossil fuel supplies and how that's related to increasing energy prices. So I won't go into it in detail today, except to note that over the last 10 years or so, net oil exports from the top 20 OPEC exporters have about stabilised despite demand increasing. So we have supply here and the demand represented by price here. And indeed, if you look at other fossil fuels such as thermal coal, liquefied natural gas, because of the growing demand in nations such as China, the prices of those are going up. Thermal coal has tripled in price over the last 12 months. If you look at who's doing most of the emitting now, historically it's been countries like the US and the EU. Developing countries like China, with a huge population base, have quickly caught up, and now China's the biggest emitter overall. On a per capita basis, China is still way down there. So there's China, there's the US, there's Australia. So you can see on a per capita basis, the energy demands are quite geographically skewed as well. Some countries, like the Republic of Congo here, almost all of the emissions, which are incredibly high, come from land use changes, whereas other countries, almost all of them come from fossil fuels. So I've talked about this scenario in a previous talk. Essentially, it's a growth of emissions outstripping our predictions of just 10 or 15 years ago, essentially because of the great development in developing world such as China. We're seeing an increase in the demand for carbon energy because it's the cheapest form of energy, such that energy intensity is actually going up. So we're using more carbon to generate $1 of GDP, and we're using more power to generate that $1 of GDP as well. So we're hungry for energy and we're more hungry for carbon, and so carbon emissions are increasing at a great rate. And then a recent analysis published by the Global Carbon Project has shown that if you take account of all of the human causes of emissions, which are about 10 billion tonnes of carbon per year, about 7.5 billion tonnes from fossil fuel emissions and about 1.5 billion tonnes from land use changes, then about 46% of that is hanging around in the atmosphere for many years. About 29% is being sunk into terrestrial sources, so more growth of plants, for instance, sequestering this carbon in their tissues, and about 26% is going into ocean sinks. So the ocean continues to absorb this carbon. But overall, the trend is worrying because the amount of emissions being sequestered is declining over time. So if we went back to the 1950s, for every tonne of emissions, about 400 kilograms would have been sequestered by these sinks. Now, about 600 kilograms, about 400 kilograms would have remained resident in the atmosphere. Now about 550 kilograms is sunk and about 450 stays, and that's continuing to rise. So we've got this decline in the ability of the atmosphere to sink carbon and the terrestrial biosphere in the oceans. Now, on the basis of different emissions pathways, I've talked about this in previous discussions, a lot of the uncertainty in climate science about how hot the planet is going to be relates to these uncertainties in human decisions about where the emissions pathway are going to take us. Are we going to follow the business of usual pathway, which, if not constrained greatly by fossil fuel limitations, risks taking us by 2100 to 5.5 to 7 degrees of global warming, up to 11 degrees of global warming by 2200, that's sort of the equilibrium level. Or if we act really rapidly and early, then we may be able to limit it to 2 to 3 degrees of global warming, which, as I've described last week, will still have major impacts that we're going to have to adapt to. This is a slide of the European heat wave of 2003. It just gives you an impact of how things that cost economies and cost society greatly, such as a heat wave, which causes deaths and great medical costs here, will change in frequency as the temperature goes up. So a projection of temperature in summer for Europe, this is a historical record and model simulations. That's the European summer heat wave of 2003. By about 2040, it'll be an average summer. By about 2060, it'll be a chilly summer. So that's the sort of impacts that are going to increase in magnitude. We're also seeing increasing insurance costs related to climate change. A recent study has shown that the intensity of tropical cyclones has increased over time, but also, irrespective of climate change, the fact that more and more people are building costlier settlements around the vulnerable areas means that insurance costs are continuing to increase exponentially. So these are costs, these are environmental impacts that are not being properly costed. Of course, if we follow the business as usual pathway through to its bitter end, then we get to a scenario like this. This is a projection globally for 2050 and 2100. We've gone 2.5 degrees of warming by 2050, 5.5 as the average by 2100. That translates to 28 degrees of warming in the Arctic, not an area where the global economy is going to be particularly stable. Indeed, if you look at it in the long-term context, then society has developed in what's known as the sweet spot of climate. The climate's been cooler in the past, it's been much hotter in the deep past, it's projected to be much hotter again. That's not a situation that society has evolved to cope with. So we're going to be testing the limits of our society to cope with these changes by imposing these new trends. That's the adaptation challenge. The mitigation challenge is to minimise the amount of those extra challenges we face. So in Australia we've seen continued warming and we've seen a drying period since the wet period of the 1970s. These have been adaptation challenges already that we've had to face. Irrespective of whether that drying is related to climate change directly, it's been a challenge that the Australian economy has had to cope with. We've had the report recently released by Ross Garnaut, the Garnaut Climate Change Review, which attempts to assess the impact, the cost impact of climate change on Australia and the cost of mitigation. And Gavin and David have talked about the CPRS, the Carbon Pollution Reduction Scheme, which is right now in green paper form. So it's an ideas paper essentially released by the government to talk about the shape of its emissions trading scheme. I'll talk more about both of those documents a little later. The Garnaut Review has produced reviews such as this, which looks at, for different temperature changes, impacts on different sectors of the Australian economy. You can do a similar thing globally. The IPCC has done this to show that for different levels of warming you'll get different amounts of impacts, and they will have relative economic impacts that increase in magnitude exponentially as temperature goes up. So at less than 1 degree there are adaptation challenges, but we should be able to cope with those. 2 to 3 to 4 degrees and it becomes unbearably difficult to cope, and we have to sacrifice many things that we would otherwise rather not lose. If you're looking at particular sectors of the Australian economy or the Australian environment that are likely to be most vulnerable to climate change impacts, then there's those that are simultaneously exposed to these impacts, more exposed relative to other sectors, and are sensitive. So that gives you the potential total impact. And then when you understand the adaptive capacity, some systems are quite adaptive, other ones have a very narrow range of adaptation. That's how you arrive at this concept of vulnerability. So not every economic sector is going to be equally vulnerable. Not every element of the Australian environment is going to be equally vulnerable. Some will benefit, most will not. This is a new way of looking at the IPCC figure on impacts of climate change across different sectors: water, ecosystems, food, coastal impacts, health, and extreme events. I'd encourage you to download the slides and look at these in detail, but the key message here is that these are projected impacts. This is where we're heading right now if we can really have a major impact on carbon emissions. So 80% reduction by 2050. This is the impacts we could expect by 2050, 2100, in that band there. Over here is if we could stabilise at emissions at 2005 levels. So when David talked about the stabilisation wedges, if we could just hold it there, we'd be up to this level of impacts, around 3.5 degrees of warming and all of the problems this entrains, unmitigated impacts, and we're here or above by 2100, which is essentially unadaptable. That's on a global scale. On a regional scale, it's also been broken down into different continents here, and small islands and polar regions. Here's Australia. This is what the Garnaut Review has been concentrating on in particular. I'd encourage you to download the slides and look at those in detail, because it's quite a fascinating analysis of what we can expect under different mitigation scenarios. There will be global disparities in relative impacts as well. Here's just one example on agriculture. Overall, because a lot of the industrialised nations tend to be in cooler realms for various historical reasons, it's projected that they may well benefit agriculturally overall from an increase in temperature, small increases in temperature at least, and an increase in atmospheric CO2. Whereas the world overall will not benefit because there's a huge deficit in developing countries, especially in places like Africa, because of the effect of drought. The effect of increasing temperatures will greatly offset the benefits of increased carbon dioxide as a natural fertiliser effect. For options for Australia in terms of mitigation, this is the business as usual pathway in terms of carbon emissions, and here are a couple of mitigation options. This is a figure from the Garnaut report, and it shows that really we're going to have to take quite a divergent pathway very soon in order to get down to the sort of emissions levels that are going to avoid 450 parts per million. 450 parts per million is looking at around 2 to 4 degrees of temperature change. So it's really too much already. But if we're going to avoid that, we have to get down to these sort of levels, which for Australia on a per capita basis, we have high emissions. It's around 90 to 98% reduction. So if you look at it globally as a contraction, so everything's contracting, and convergence, everything's converging on this one point, then nations like India, which on a per capita basis have very low emissions, less than a tonne per person, there's actually some scope for them to increase their emissions to reach that global target of 450, whereas for Australia you can see the fall is greatest because we've had this historical dip. In terms of dependence on fossil fuels and whether they'll get us out of the problem, Michael Lardelli will talk about that next fortnight. Essentially, there's enough coal and oil remaining to take us to climate purgatory, and yet there's probably not enough oil and gas remaining to take us to the sort of scenarios that is the worst case scenario, business as usual. We're going to run out of those before we get to that point. So we've got this nexus of problems of energy supply from traditional sources and the problems that continued utilisation of that right to the bitter end will cause for climate. So this concept of cap and trade or tax, and I like that figure of the invisible hand of the market. Without some regulation, that's what it will do, and we can see that in the current financial crisis. And we can't just ignore the problem as well, so we can't go for offshore sequestration of coal like we're doing at present. Emissions cap and trades and carbon taxes are a complex issue, and they have pros and cons. I've tried to summarise some of the elements here. A cap and trade system, which is what the Carbon Pollution Reduction Scheme aims for, is to ensure a falling emissions profile. That's the theory, at least, that if you have set a cap and then you reduce that cap over time, emissions will fall. Unless, of course, you're not covering every part of the emitting sectors, and that's the case right now, or if the government gets overt pressure on them and doesn't reduce the cap fast enough, that can be another problem. But that's the theory, at least. And the other theory is that it should reduce inefficiencies and overpricing because it creates both incentives and disincentives for abatement. So by doing the right thing, you're reducing your emissions and you're then able to sell your remaining permits on to those who aren't able to do the right thing, or at least not as effectively, and make money out of it. The cons include things such as enriching middlemen and brokers. By introducing this scheme will require an army of bureaucrats and an entirely new management system, a carbon bank, in order to manage this. It will come with costs. It encourages rent seeking and pleading from special interest groups. I'm seeing a lot of that right now going on in Canberra. And there's a limited price certainty involved in the cap and trade system. We don't quite know how much the cost of a carbon permit will be. So at the very least it requires these gateways, which are defined maximum carbon prices that a government will set out to, or at least defined caps that a government will set out every few years that they sort of ensure that the price won't go beyond that to give businesses some security. For a carbon tax, on the other hand, then that will involve politicians or bureaucrats, seems never scientists will set the costs, and that has the risk of introducing inefficiencies and overt pressures that are unnecessary, because if the cap's set too high and it causes real market problems, including financial collapses, then that's obviously a major problem, and it's hard to know quite what the price would be that would generate that. And there's no guarantee that emissions will fall. You could continue to increase the price, you could double the price of petrol, people will continue to drive cars. So there needs to be other mechanisms that come into play to actually encourage emissions to fall. I'll talk a bit more about that a little later. The advantages of a carbon tax, however, there's quite a few of them. I'm actually in favour of a carbon tax rather than a cap and trade scheme, but I can see advantages in both. It provides a clear forward price projection, so investment certainty. The government can specify what the carbon tax will be for a certain number of years out, so a company can look at its total emissions, calculate how much they're going to pay without uncertainty about what the carbon price will be on a year-to-year basis, and they'll know what the business risk is. So it removes the incentives for things like hedge funds and derivatives, all of these risk-based systems that are set up essentially to manage financial risk. They can, in a carbon tax system, they can go away, at least for that sector of the economy. And so it better allows for long-term business planning. It can essentially use the current tax system, so you don't need to invent the new carbon bank. And it has the potential to better handle things such as emission-intensive trade-exposed industries, because you can simply apply a carbon tariff at the trade gate rather than worrying about whether permits are valid across that trade gate. So in terms of global greenhouse gas emissions, they've obviously risen dramatically since the 1970s. If you look at what's contributing to those in terms of different economic sectors, energy supply, transport, industry, forestry, agriculture, they're the big contributors. They're the ones that are going to have to make the cuts. This concept of stabilisation wedges can go beyond stabilisation to emissions reduction wedges. If you look at it very simply and you look at the amount of carbon produced by electricity and transport and heat generation and agriculture and so on, you've got growing demand and you want to reduce this to some point in the future, then you have to look at ways of replacing the energy supply or else sequestering the carbon. So renewable energies is one way of replacing the energy supply, energy efficiency is another way of replacing the demand for energy, and sequestration is a way of reducing the amount of carbon that gets into the atmosphere as a result of generating that energy. You can look at it in terms of breaking down these individual wedges, as David's talked about. I don't need to go into those in detail. Essentially, it looks at breaking the problem down into many different components that are each manageable. If you look at the demand for energy in Australia, then and the cost of energy, then this tells us a lot about where we can make good gains. If you look at disposable income and how much different income brackets spend on food and car fuel, gas and electricity, then a lot of the spending actually of disposable income goes on food. So food price changes are going to impact us more heavily than electricity or car fuel or gas. Overall, Australia doesn't pay much for energy compared to other nations. If you look at our costs here compared to for residential and industrial compared to things such as the Slovak Republic or the Netherlands, then we're less than half the cost of that. So we've been living off cheap energy because of coal. So it's been cheap, environmentally unsubsidised energy. So to argue that economies can't function at a higher energy price is not supported by a global analysis. In terms of what a carbon pollution reduction scheme or a carbon tax would do, yes, it's going to have effects that play out throughout the economy. They're difficult to predict because there's so many possible interactions, and it's also difficult to predict how quickly those will stabilise and then benefits will start to accrue as people do things cleverly. So if you increase the cost on paying for coal mining and increasing higher coal prices, higher electricity prices, these will cascade through the economy and eventually it'll come back to households. But there are a lot of gains we can make actually that we're just not pursuing right now because it's not worth our bother or because there hasn't been sufficient regulation to allow this to happen. This is a result of the McKinsey report on carbon abatement in Australia through to 2030. Here's a 2020 scenario. What this graph does is look at cost of abatement in tonnes per CO2 emitted, where 0 means it doesn't cost you anything, negative means it saves you money, and positive means it costs money to do it. So there are all these measures we can implement straight away in terms of energy conservation, doing things more cleverly, that save us money, and then there are these things that cost more and more depending on what we try. So right now, solar photovoltaic, for instance, is really expensive, and if you wanted to replace Australia's energy supply now with solar photovoltaic, you couldn't do it. It would cost too much. But you can do all of these things straight away and reduce our emissions by between 10 and 30% without costing the economy $1. It's just a matter of a bit of forward thinking in terms of payback periods to do it. And a lot of these other abatement schemes can reduce large amounts of carbon, so the width of the histogram there represents the amount of carbon it can save at a fairly low cost. So in other words, we can do things now and we can do things in the future. We've got to pursue both of these options. Energy efficiency is the most important one immediately. In the long term, replacing our energy supply to ensure that we continue to have a growing energy supply will be the key to continued ongoing growth. Now, to balance the cost of doing something about it, climate change in terms of changing the economy around to different energy sources, we need to consider the impacts, the cost of climate change that's unmitigated. This was another mandate of the Garneau Review. So he broke it down into 4 different impacts of climate change. Currently measurable market impacts that are not currently measurable, but if we get our act together we might be able to measure them in the future, insurance value against high damages and extreme events, and then non-market impacts such as a species going extinct or someone having their lifestyle affected. So they're the 4 different things that could possibly impact it. This is a result of the Garneau Review, where this is the growth in an imaginary fantasy world where we could continue business as usual and not have any climate change impacts. And then these are the costs in terms on the economy of climate change impacts, and that's the bottom line. But guess what? That's that part of the graph. So all Garneau's done is costed the measurable market impact, and he said we can't cost the others, so they're going to be additional to it. So that's the impact of the measurable ones right now. So you add in a whole lot more and it quickly starts to look pretty nasty. The concept of mitigation versus adaptation is well illustrated by this slide from the Garneau review, where here's some measure of utility, whether it be the amount of income you can earn or the value of the tourism industry, whatever you can think of in terms of an economic utility. Then as you increase mitigation into the future, then the utility could continue to rise, but at some point the costs will go up if you implement a scheme such as a carbon pollution reduction scheme. So you have this disparity early on where it costs more to do something about the problem than to ignore it. But then you get this crossover point at which, and depending on the amount of impact, that crossover point can come later or earlier, where by ignoring the problem it catches up with you. Now in many sectors it's catching up with us already. That will continue to occur. The risk is that once it's caught up with us, then the costs quickly outweigh the benefits. This is a table from the Garneau report looking just at one sector. It's looking at costs in 2030, 2050, 2100 on damage to the productivity of the Murray-Darling Basin. So in that case, we've got a no mitigation scenario. This is business as usual, 550 parts per million, 450 parts per million, and sort of a bad luck story if climate turns out to be more sensitive than we'd imagined. Well, at no mitigation, you're looking at 92% reduction in agricultural productivity in the Murray-Darling Basin by 2100, whereas at the cost of reducing emissions to 550 parts per million, it's down to 20%, or 450, it's down to 6%. So you can see there's a big gain there, obviously, if this is correct in terms of mitigating, but the gain doesn't really come early on. Most of the disparity comes later on. In that case, most of the impact will come in terms of dry land, farming, grains and cattle and dairy and so on. Now, this is a figure concentrating on South Australia, and it's looking at why we're vulnerable to climate change. We've heard a bit about this already from Peter Heyman a few sessions ago. If you consider Goyder's line and the fact that this may shift, that means that the amount of the state that's agriculturally productive is going to shift. Now, how much will that shift? Well, it depends on the scenario. If we look at average annual rainfall in South Australia over the last 50 years or so, then it looks something like this, where we have the arid north and the mesic south, very wet around the Mount Lofties and the southeast. That's essentially Goyder's line, above which cropping becomes impossible. At a sort of mid-range rainfall scenario, by 2050, it could look like that. So it's gone from that to that. That will have an economic impact on the agricultural sector, as well as having an impact on the amount of water availability in areas such as the Mount Lofty, which supplies most of the water for Adelaide. Overall then, when you introduce something like a carbon trading scheme, you're going to have an immediate economic impact that's going to cause a reduction in the gross national product. So here it's modelled as from the Garneau report again, that you have this drop-off of about 0.8% of GDP in the first year. Then that quickly stabilises, so you don't continue to get declines. And eventually, at some crossover point, you start to get these net benefits. So it's not like it continues to be bad news. It has a hit, then it stabilises, and then you start to gain. In terms of how much you might lose out, you could look at it this way. This is total after-tax per capita income for Australia in 2005 dollars. So it's projected to be, on the reference case, this is the case for business as usual without climate change impacts, then 36,548 in 2006, with continued economic growth up to 42,000 by 2020, 60,000 by 2022. These are in current dollar terms, so they're adjusting for inflation. So you'd expect people to be about twice as rich by 2050 at current rates of economic growth, if there was no climate change impacts. If there was climate change impacts, then that could actually continue to, that could grow and then decline, and in the end we could be earning very much less. But let's look at a couple of the mitigation scenarios. 550 parts per million, 450. We're not looking at economic ruin. We're looking at going from 36,000 to 42 to 60, to 36,000 to 42, or it's $500 difference there, to 56 there, it's $4,000 difference there. At the rate of economic growth, you make it up in about a year. So we're not talking about ruining the economy, and I think the other speakers have also made that point quite clear. Okay, but how do we actually get to reducing our emissions by 60% or 80% or 90% or 99% or 150% by 2050? How do you get there? Well, renewables are one obvious option, but can they scale up to the degree that would actually be required? Well, if you look at total energy resources, then the little blue box there is energy consumption by humans, and these are oil and gas and coal supplies. Lots of that left. How much of it is accessible is the big open question. That's a question about peak oil and peak gas and coal. How much can we actually extract economically? Then if you look at solar energy, then there's a rather large amount, and that doesn't get used up. It comes back every year. And of course hydro and wind are all part of the solar energy mix, in fact, because it's all driven by power from the sun. So there's a lot of energy out there. So the question is not how much energy is there, it's whether we can tap it, and whether we can tap it economically. This is one vision for an emissions profile, an energy profile for Australia through to 2100 from the Garneau review here. So it's looking at terawatts of energy generated. This is where we are or where we'll be in 2013, so about 15% renewables, the rest made up mostly of coal and gas. This is envisaging a decline in coal through to essentially its elimination by 2030 to 2040. A pickup, optimistically, in carbon capture and storage of coal, so it continues to have a role, especially around mid-century, and gas. But then this massive expansion of non-hydro renewables, solar energy, wind energy, geothermal, and so on. So this is not envisaging a restriction of energy in the long term, it's envisaging a growth in energy, but a growth from different sources, renewable sources. How feasible is this? Well, there's been a good example in Australia so far has been South Australia, where we've seen this massive increase in wind power, where now South Australia supplies over 40% of Australia's wind power, with 8% of the population. So we're doing more than our fair share, and there are huge wind resources available, especially in areas around the Eyre Peninsula. Down here, there's very strong winds. They're the best places to build. Now, ironically, we're not building wind farms there because they're away from the electricity grid. So what you need is a high voltage direct current line to connect up this part of the coastline with where the energy supply is required. But it does show that this has been one area where we've had exponential growth in renewable energy supply. Exponential growth, perpetuated for many years, results in a huge change. Now, solar resources, as I've said, are potentially massive. The best places for solar energy are in Australia, Saharan Africa, and the western part of the United States. They're the areas of highest incident solar radiation, which is perfect for things such as solar thermal, solar concentrating power. These are not the photovoltaics that you put on your rooftop, the ones that generate electricity directly. These are ones that use the energy of the sun to heat oil, to drive turbines, essentially, to produce electricity, very much like other forms of heat generation technology such as burning coal do. Now, Australia has a lot of energy at its disposal. These squares represent, if you were to take current technology of solar concentrating power, it's about 20% efficient, and carpet a certain amount of the Australian desert with it, and how much energy you could supply. Now, that's putting aside cost. It would obviously be hideously expensive to do it at current costs. But in terms of energy supply potential, then you would require that area to supply all of Australia's needs in 2020. That would supply the US's needs, that would supply China's needs, that would supply China's total energy demand, including liquid fuels, and that would be the total global supply of energy in terms of electricity and liquid fuels for the world in 2020. Obviously, we're not going to do that, but it gives you an example that there are plenty of resources out there, not just in Australia, but in Saharan Africa, in Western China, in the United States, and so on. And we're not just going to focus on concentrating power. We're going to focus on the wind down here and the wave generation capacity, geothermal energy, and so on. So the idea of a diversified energy supply is key because the sun isn't shining all the time. Australia moves out of sunlight at night, and obviously you're not going to generate power supply then. So there's a need for essentially batteries, and batteries in the form of things such as molten salts, which can store heat for up to 16 hours. So that would provide baseload power, and also other technologies such as compressed air batteries, so that you essentially use a generator to store energy in a potential energy form that's released as kinetic energy when you need it. The peak load demands for energy in hot days, for instance, are at the peak supply times for solar, so it obviously provides a great backup for wind, because if you look at here in the Adelaide heat wave, then the demand for energy was often greatest when the wind wasn't blowing. So just using wind to provide energy was not going to be sufficient to meet all those air conditioners turning on. Geothermal would be, though, because geothermal is one of those baseload renewable energy sources of which there's huge interest in Australia because we have a large amount of geothermal resources. These are hot, dry rocks about 4 kilometres under the Earth's surface. They're mostly granite and other igneous rocks like that are heated by the breakdown of radioactive particles. So that happens over millions of years and it heats the rock. So ironically, it's nuclear energy in a natural form. You pump water down to these rocks, you heat it up, and it comes back up as hot water, steam, and that drives a turbine. And because that's not dependent on the sun shining or the wind blowing, that's base load power. It will continue to supply power around 90 to 95% of the time. So if you implement geothermal energy in combination with some of the intermittent renewables, you start to get a diversified supply that can continue to supply large amounts of energy. It's been estimated that Australia's geothermal resources are sufficient to meet our projected energy demand for at least 200 years just on that supply alone. So that's a lot of energy to tap. But of course there's convergences of technologies as well that we need to consider. The best hot, dry rock resources happen to be located in the same spot where the best solar resources are. So if you can change the energy grid from those blue lines there, which is the current energy grid, and connect them up through high voltage direct current lines, which have a very low transmission loss of about 1 or 2% per 1,000 kilometres, then you start to have a connected grid which allows for load balancing and a more efficient supply. It's been estimated it will save about $1 billion just on load efficiency alone. Then you start to get a grid that's well connected and is linked up to these areas of dual supply. So wind and wave over here, solar and geothermal over here, and so on. Enough energy to supply the Australian economy, and indeed, if you really want to start to imagine, start to pipe the energy north. And that concept has been adopted by initiatives such as TREC, which is power from deserts, essentially. It's looking at large solar thermal arrays in the Sahara here, wind resources right along the African coast and European coastline, biomass generation within Europe, geothermal access in Iceland and throughout Europe here, a connected renewable grid that would supply energy for Europe and Africa. Other renewable sources that have huge potential but we just don't know how scalable they are wave power. This is another baseload form of power where it's using the surge of the ocean, which is sufficient about 90% of the time to provide power. This particular technology, CETO, is being developed in Australia. It's gone through a couple of stages of demonstration. What it does is these buoys go up and down in the surge and they pump water onshore at high pressure. That can be forced through a membrane to desalinate directly rather than using energy to do that, electrical energy, or it can turn a turbine and generate electricity. And you want more energy, you put more buoys down. So it's infinitely scalable. And in terms of replacing liquid fuels, if we've got this oil crunch, either here now or coming soon, then we need to look at alternative supplies of liquid fuels or move entirely to electrical vehicles. But there's some great potential in second-generation biofuels and third-generation biofuels. Here's second-generation biofuels, which is microalgae. These are tiny microscopic plants that grow in water. If you can feed them a concentrated stream of CO2, then they can potentially generate huge amounts of biodiesel, which can be used in vehicles. A bit like the solar thermal, you can estimate that an area carpeted with these sort of ponds 60 by 60 kilometres could supply all of Australia with its liquid fuel needs. There's a lot of technological development that needs to continue to go in there, but there's huge potential. And if you look at the biofuels issue, most of them are not particularly green. They require large amounts of fossil fuel energy inputs in order to make them effective, but that's not the case for microalgal biodiesel. where if you look at the greenhouse gas emissions, almost all of these are positive, soybeans and switchgrass and sugarcane and corn, and they have high inputs of fertiliser and water and so on, and they would require unrealistic amounts of land in order to supply energy. This is to supply half of the US needs. For corn, you'd need to have double to triple the land area of the US to do it. Whereas for microalgal biodiesel, you might need 1 or 2%. And so the greenhouse gas emissions reduction would be incredibly low. We're not there yet, though, but the technology is developing rapidly. There's cause for hope. So that one is obviously, if you're going to go for biofuels, that's the no-brainer option. In terms of costs right now, coal has been supported historically so that it's cheap. We know how to do it. The technology's been well tested. The coal-fired power stations have been subsidised by governments for over 100 years. It doesn't cost much to start to generate power once they're built. So we've got a cost of coal down here, and there's no environmental cost being paid. Nuclear requires a large input to get them up and going, but the costs are not too bad. Once you start to add carbon capture and storage, and coal moves up to here, gas moves up to here as well, this is where the renewables sit right now, sort of in that band of 120 down to about $50 per megawatt hour. So right now they're not cost competitive with coal, but coal is unrealistically priced in a number of ways. Once you start to realistically price coal, bingo, they start to become cost competitive. And if you look at it in terms of an innovation chain, then you have different technologies that move along this chain. Initially there's a supply push here, and then there's a demand pull. So you need incentives early on to get this research going, and eventually the markets start to suck it up, and that drives a lot of the innovation. Where are they right now, these technologies? Well, biodiesel and coal carbon capture and storage, geothermal, they're in this early stage R&D. Whereas wave power is starting to do commercial demonstrations. Solar concentrating power in some areas of the world has been supplying power regularly for 25 years. So it's at this stage of commercialisation. It's not at the stage of high market uptake. So if you really want to get to diffusion across the market, where wind's actually starting to get there, then you need to have the right sort of incentives, such as a carbon price, to get them there. If you look at why we think it's realistic that the cost of these things will continue to go down and their cost competitive will go up, there's this idea of the marginal cost of producing through new technologies. It starts off as hideously expensive because it's a new technology. We don't know how to do it. We don't know how to upscale it properly. We don't know whether it can be upscaled, so there's huge risks. But there's a steep learning curve, and eventually that starts to level off. Now, you put a carbon price on something like coal down here, so you shift it up a bit, and what do? You move it back. So you just make those technologies become cost effective earlier than they would otherwise be. They're going to get there anyway. We're going to run out of these fossil fuel supplies. The cost of these renewables is going down rapidly, but what we want to do through a carbon price is make sure that they're picked up even faster than they would otherwise be. If you look at the history of renewable energy costs for wind and photovoltaics, geothermal, solar thermal, biomass, they've been going down exponentially over time. This graph, which is a little hard to see there, is since the 1980s. So they've been going down exponentially. There's no reason why they won't continue to go down with research and innovation. If you look at why they go down, there's various reasons. The factors contributing to cost reduction include efficiencies, when you start to learn how to scale them up, volume productions, as you start to manufacture more of them, the prices go down, and technological development. So this is the innovation step that makes things easier to do, more cost effective to do. So at current Australian energy prices, if you put carbon capture and storage, or for pulverised coal, is the cost here, or a carbon tax or carbon emissions trading scheme with no price, you bump it up to about, at a $40 a tonne, $30 a tonne, you bump it up to around 8 to 9 cents a kilowatt hour. Whereas concentrating solar power, it's up at around 12 or so right now. That will drop under a carbon price earlier than 2015 to be cost competitive. Without a carbon price, it might do it, if we're looking at around down here, it might do it by about 2025. So what it's doing is it's accelerating the rate at which it catches up. In a long term, the prospects are that concentrating solar power, geothermal, they will be considerably cheaper than coal. And it's going great guns already. This is not speculative technology. Concentrating solar power and solar photovoltaics are increasing dramatically. It's concentrating solar power, which has the potential for industrial scale power generation rather than just rooftop scale Mickey Mouse generation, at least with how solar photovoltaic technologies have currently evolved. That's the one that's now increasing exponentially. That's the one you can expect to take off. If you break it down in a table like this, I had a graphic similar to this earlier. Solar thermal, wave, wind, geothermal, biomass. The costs per megawatt hour, they range depending on the cost estimates. The cost of coal with carbon capture and storage or gas with carbon capture and storage, and you can see they're very similar then to these current costs of these technologies, or coal with a $40 a tonne carbon price. Not much difference then across all of these at today's prices. The lead-in time for really developing these on a large scale is 2 to 5 years for solar thermal, because the technology is essentially here. Same with wave. Wind, it's obviously delivering now, and it's just a matter of putting more turbines down. Geothermal, depending on who you talk to and how much investment there, maybe 10 or 20 years. Biomass, there's a lot of potential for rapid uptake of that. Coal, carbon capture and storage, depending on investment in that technology, 10 to 20 years off. The cost reductions are across all of these renewables, up to 5% per annum for solar thermal, but prices are going down in all of these. The cost of coal is rising as it's a finite supply and demand continues to rise. And with the carbon price increasing as the cap goes down, the price will continue to go up. Carbon capture and storage, well, hey, that's still dependent on coal. So the price isn't going to go down again. So that's a sort of powerful argument for suggesting that it makes economic sense to invest in these technologies. Somewhere like South Australia, it makes sense to start investing in places where there are synergies for these technologies, such as around the northeast of the state, where we have this confluence of geothermal and solar thermal technology. Down in the Eyre Peninsula, we have abundant wave resources and wind resources. Around Adelaide here, would be a great place to build a microalgal biodiesel plant around the Torrens Island gas-fired power station, which can supply a concentrated stream of CO2. And we have wind power around there already. That's already on the grid. Down here in the southeast, there's also potential for geothermal, wave and wind. They're the sensible places to put your money for venture capitalists to invest, to connect your high voltage direct current lines, because they're the places that are going to deliver multiple benefits. Now, if you don't believe that we can do this, then just reflect on innovations in a few other technologies that we know have been proven up. Let's consider storage in computing. That was what you needed to do to store a bit of computer data in the 1950s. You needed a crane to load onto an aeroplane. Well, by the 1980s, it had become sort of 1 million times cheaper and could store 1,000 times more data on that little floppy drive. And now, we go on another 20 years or so, and we've got these tiny USB drives that can store 1 million to 10 million times more than that, and they cost a hell of a lot less. So that's an example of how the innovation chain works. Communications technology is another one. It's an old-style phone. You needed a backpack to carry around a mobile phone in the early 1980s, and we got clever and were able to have these wonderful portable devices and Helix Shaft. And now we've got devices like this, which look extraordinarily similar to Captain Kirk's communicator, which was projected for 2250. So that's another example where once the market pull started to take over from the supply push, then things started to happen very quickly. Now that's my prediction with renewables as well. That's our best bet for getting out of the climate problem. If you want to do things yourself, of course, the steps you can take immediately, obviously you can't read all the details on there, but if you go to my website, I've got that one posted there, which is a poster that I produced for World Environment Day this year, which is looking at the 10 best ways to reduce your own personal carbon emissions. You can do things now, especially in terms of lifestyle choices and energy efficiency, that can make big gains, as well as providing political input and incentives to invest in renewable energies. We do have the situation where, even with all of that effort, that may not save us from some very unpleasant climate impacts. That's where people start to talk about geoengineering. Speculative ideas such as putting 16 trillion mirrors in space at the Lagrange point of equal gravitational pull between the Earth and the Sun, or simulating the volcano effect by having high altitude planes or balloons spraying sulfate particles in the stratosphere each and every year to cool the planet, or building artificial trees, or ideally genetically engineering bacterium that can sequester huge amounts of carbon. None of these are ideal. One would cost a hell of a lot, and is potentially not able to be scaled up. You'd have to build those mirrors at a rate of about 10 times the US currently produces bullets for its army for 15 years in order to do that. So it doesn't seem all that feasible to me. This one, I think, is most likely to be implemented in connection with carbon reduction, because if you try and use that as the only solution, you don't solve ocean acidification, and you need to put a lot of sulfates up there. So it causes acid rain problems, deterioration of ozone, and a drying of the atmosphere. But if you only need to mitigate the warming slightly, in other words, if you've implemented massive carbon reductions, you're still a bit hot and you want to cool it, then the effects are much less. And in fact, when they're modelled in that way, it's not that expensive. That may be the sort of geoengineering solution we need to reach for in order to ensure that we have an adaptable climate. Because what we're aiming for is to manage the unavoidable, that's adaptation, and avoid the unmanageable, which is mitigation and developing our new energy supply. So for more information on this talk, as always, log on to the website and make your voices known. And I'll of course continue to update and post about these ideas into the future. But now we'll take a little time before we have to close for a few questions. Thank you.